How do bullets work? Has any other single invention changed history quite so much as explosives? As the power behind bombs and missiles, chemical explosives have made possible most of the great wars of the last 1,000 years or so, altering the course of history time and time again. Before the invention of gunpowder, the first chemical explosive, people had to fight their enemies hand to hand on the battlefield with crude weapons, like swords and spears. Today, you don't even have to be able to see your enemy, let alone touch them. It's easy to drop bombs from airplanes, shoot them from submarines, or launch them on rockets from one side of the earth to the other. But even though modern missiles are incredibly sophisticated, the basic science and technology behind them is pretty much the same as it was 1,000 years ago. What's inside a bullet cartridge? When people talk about a bullet in everyday language, they often mean a cartridge, which is a three-part vehicle with the actual bullet mounted on the very end. The cartridge is the thing you load into a rifle. The bullet is the part of a cartridge that fires out the end. Cartridges are a bit like fireworks, and they are arranged in three sections: the primer, the propellant, and the bullet proper. At the back, the primer, or percussion cap, is like the fuse of a firework, a small fire that starts a bigger one. The next section of the cartridge, effectively the bullet's main engine, is a chemical explosive called a propellant. Its job is to power the bullet down the gun, and through the air to the target. The front part of the cartridge is the actual bullet, a tapering metal cylinder that hits the target at high speed. It tapers to a point mainly to reduce air resistance, so it goes faster and further, but also to help it penetrate metal, flesh, or whatever else the target may be made from. It must penetrate the target before it can do damage. What happens when you fire? Bullet cartridges are designed to be relatively safe until the moment when you fire them. When you pull the trigger of a gun, a spring mechanism hammers a metal firing pin into the back end of the cartridge, igniting the small explosive charge in the primer. The primer then ignites the propellant, the main explosive that occupies about 2/3 of a typical cartridge's volume. As the propellant chemicals burn, they generate lots of gas very quickly. The sudden, high pressure of the gas splits the bullet from the end of the cartridge, forcing it down the gun barrel at extremely high speed. 300 meters per second, or 1,000 feet per second is typical in a handgun. It's only the bullet that fires from the gun, the rest of the cartridge stays where it is. It has to be ejected after firing. Sometimes manually, sometimes automatically, to make way for the next cartridge, and the next shot. The propellant chemicals in a handgun cartridge are not designed to explode suddenly, all at once. That would blow the whole gun open, and very likely kill the person firing it. Instead, they are supposed to start burning relatively slowly, through a process called deflagration, so the cartridge moves off smoothly down the gun. They burn faster as the bullet accelerates down the barrel, giving it a maximum kicking force just as it comes out of the end. As the cartridge emerges, the whole gun recoils, leaps backward, because of a basic law of physics called action and reaction, or Newton's third law of motion. When the gas from the explosion shoots the bullet forwards with force, the whole gun jolts backwards with an equal force in the opposite direction. The explosion that fires a bullet happens in the confined space of the gun barrel. As the bullet flies out of the gun, the pressure of the explosion is suddenly released. That's what makes a gun go bang. It's a bit like uncorking a bottle of wine at much higher speed and pressure. Some bullets also make noise because they go so quickly. The fastest bullets travel at around 3,000 kilometers per hour. Over 1,800 miles per hour, about 3 times the speed of sound. Like a supersonic, faster than sound, jet fighter, these bullets make shock waves as they roar through the air. How bullets travel. Gun barrels have spiraling grooves cut into them that make bullets spin around very fast as they emerge. A spinning bullet is like a gyroscope, a sort of stubborn spinning wheel that always tries to keep turning the same way. If you try to tilt a gyroscope while it's spinning, it will try to resist whatever force you apply, and if you let go, it will soon tilt back the other way. This is why, when things are spinning, they are very hard to deflect from their path. We call this idea gyroscopic inertia or stability. A bullet behaves in exactly the same way. Once it's spinning, it follows a straighter path as it goes through the air, so it's harder to deflect, and much more likely to reach its target. We think of bullets flying in perfectly straight lines, but nothing could be further from the truth. Several different forces act on a bullet as it goes through the air. Over very short distances, bullets do follow more or less a straight line. Over longer distances, they follow a slight downward curve because gravity tugs them toward the ground as they go along. Air resistance and the spinning, gyroscopic motion of a bullet complicate things too. Usually, because of recoil, the person firing wobbles the gun slightly when the bullet emerges. When all these factors, the bullet's motion, gravity, air resistance, recoil, and spinning, add together, they make a bullet follow a very complicated corkscrew path as it flies through the air. Why bullets do damage? A moving object has momentum, which is the product of its mass and its velocity. The faster something moves and the heavier it is, the more momentum it has. A truck trundling along slowly has a lot of momentum because it weighs so much. Even though bullets are tiny, they have lots of momentum because they go so fast. And because they go fast, they also have huge amounts of kinetic energy, which they get from the chemical energy of the burning propellant. Remember that kinetic energy is related to the square of an object's velocity, so if it goes twice as fast, it has 4 times the energy. Bullets do damage when they transfer their energy to the things they hit. The faster something loses its momentum, the more force it produces. One way to define force is as the rate at which an object's momentum changes. A rifle bullet coming to a stop in 1/10 of a second produces as much force as a heavy, slow-moving truck coming to rest in 10 seconds. Imagine being hit by a truck, and you'll have some idea why bullets do so much damage. More energy equals more damage? It's easy to conclude from this that a bullet needs to have as much energy as possible to do the maximum amount of damage, but, unfortunately, it's not quite that simple. A rifle bullet has many times the velocity and kinetic energy of a handgun bullet, so much so that it will typically enter one side of a target, whiz straight through, and fly out the other side. If a bullet leaves the target at high speed, it's taking valuable energy with it. So what we really want from a bullet is that it deposits as much energy as possible inside the target, either stopping entirely without exiting, or leaving with the minimum possible velocity. There are various ways to achieve this. The crudest way is for a bullet to expand as it enters the target. A bullet that expands has a bigger cross-sectional area, so it creates a bigger hole, or wound, in the target. It takes more energy to make a bigger hole in something. We need to use more force over the same distance, so we say that the bullet does more work, and uses more energy in the process. Bullets can be designed to expand by making them hollow at the pointed end and, after impact, they expand, and squash down into a shape that looks like a button mushroom. That's why deforming bullets are called hollow point or mushrooming bullets. Dum-dum bullets is another common name for them, taken from the place in India where they were invented in the late 19th century. International law has restricted the use of expanding bullets like this in wartime since 1899, but some police forces do still use them. That's partly because expanding bullets do so much damage that they immediately incapacitate their target, but also because a mushrooming bullet, fired in self-defense, maybe in a crowded city street, is much more likely to stay inside its target, and less likely to injure an innocent bystander by accident. Soft point bullets work in a similar way, only using a soft lead tip instead of a hollow point, but expand more slowly, and typically penetrate deeper. How far and how fast? In theory, you can calculate how far a bullet is going to go using the equations of motion based on Newton's 3 laws. If you know how fast a bullet is going, and you assume it travels at constant horizontal speed, it's relatively easy to calculate how far it travels. The distance is the average horizontal speed multiplied by the time. How do you know the time? You can work this out from the bullet's vertical motion. You calculate how long a bullet is in the air by finding its vertical velocity. You can then calculate the time the bullet is in the air using the acceleration due to gravity. Once you have the time, you can figure out how far the bullet travels horizontally. Now, if you run the numbers through, you'll find something surprising. When rifle bullets exit the barrel of a gun, they typically have an initial speed, called the muzzle velocity, that ranges from about 2,000 km per hour, 1,200 miles per hour, or 550 miles per second, up to about 4,500 km per hour, 2,800 miles per hour, or 1,250 miles per hour. If you put numbers like that into the equations, you'll find a rifle bullet, fired at an angle of 45 degrees, ought to travel about 100 to 150 kilometers, 60 to 90 miles, from the gun. Of course, bullets don't go anything like that far. The maximum range might be up to about 4 kilometers, or 2.5 miles. How do we explain this? Drag. The faster things travel, the more air resistance they feel. For high-speed projectiles such as bullets, drag, air resistance, increases as the square of the velocity. Clearly, if their range is reduced by about 25 to 40 times, drag has an enormous effect on them. Although heavier projectiles, such as artillery shells, are bigger and bulkier, they travel considerably slower. For that reason, it turns out they're slowed down much less by air resistance, so their actual range is more like a quarter to a half of their theoretical range. What materials are bullets made from? Bullets and their cartridges are a bit of a riddle. They have to be tough to withstand the initial explosion inside a gun, and so they keep the aerodynamic shape that allows them to be targeted precisely. Yet, when they arrive at the target, they need to pierce or deform in a very particular way to cause a maximum amount of damage. So the choice of materials, the combination of materials used in different parts of a cartridge, and how those different materials stick together and separate at just the right time are very important considerations. Ultimately, all the materials used in a particular bullet cartridge depend on the job it's been designed to do. In other words, cartridges with different purposes are often very different on the inside. As we've already seen, bullets need to be heavy to do damage, so the core part is typically made from lead, a heavy, widely available, and inexpensive metal, and one that deforms fairly easily. Other metals such as hardened steel, tungsten, in armor-piercing bullets, and copper or alloys such as brass are also used, as are, controversially, very dense materials like depleted uranium. Less lethal bullets designed for things like riot control are meant to scare or lightly wound, so they typically have non-metal cores made from materials such as rubber, wood, or molded plastics. Rubber bullets, for example, often contain pellets of rubber, plastics such as PVC, or minerals in a metal outer jacket. The other parts of a bullet cartridge are also made from metals or alloys. Bullet jackets can be made from many different metals, including steel-coated alloys, and copper alloys, such as cupronickel, often with dry lubricants to help them speed through a weapon, from nylon, and Teflon to wax, and low-friction alloys such as lube alloy, based on copper, zinc, and tin, and anti-corrosive coatings, so they last longer in storage. And this is all about how do bullets work. We hope you have found it interesting.